everyone. Hello, good morning everyone. Good morning. Yes, today's topic is chapter number 4, Intermediate SQL. In this chapter we continue our study of the SQL. In the last class we also studied the SQL, but the basic concept, or we can say the base of the SQL. Now the next part is the Intermediate SQL. So we introduce a natural join operation. SQL provides other forms of join operation also, including the ability to join, including the facility to join the concept, or how to use the join operations, or whatever various ways by which we can join the concept, by which we can combine, or by which we can use the SQL, or that is the intermediate SQL. So in this chapter we introduces the concept of a natural join operation that provides other forms of join operation also, including the ability to specify explicit join predicate and the predicate, and the ability to include subtuples that are excluded by the join predicate in the result tuples that are excluded by the natural join. So we'll discuss different forms of join in this section, and the example in this section involves two relations, that is the two tables are used. One is a student, one is a takes, that is shown in figure, this one. This is the student relation, the student table. The next one is a teaches or the takes relation. So in this section we are discussing two operations, that is the natural join and the join precedent or the predicate, that the ability to include in the recent tuple that are excluded by the natural join. Then the examples in this section involves two relations, student and the takes, that is over here. This is a student, there is ID, name, department name, total credit. This is ID, name, department name, total credit. That is the student relation. Then a takes relation, this is also ID, course ID, section ID, semester, year, and the grade. Then the join conditions, we saw how to express the natural joins, and we saw the join using clause, which is a form of the natural join that only requires values to match on a specified attribute. And the SQL also supports another form of join in which an arbitrary join condition can be specified. It may or may not be specified over here. And the on condition allows a general predicate over the relation being joined, and this predicate is written like a where clause predicate, except for the use of the keyword on rather than where. That means we are using the where clause, we are using the on clause over here. Like the using condition, the on condition appears at the end of the join operation. This is one of the example. Select asterisk. Asterisk means each and everything, that is all. From student join takes. Now the student is joined with the takes on student ID equals to takes.id. That means ID of the student is equals to the ID of the takes relation. And the on condition above specifies that a tuple from the student matches a tuple from the takes if their ID values are equal. And the join expression in this case is almost the same as a join operation or a join expression student natural join takes, since the natural join operation is very useful, or also requires that for a student tuple and the takes tuple to match. But the main difference over here is the ID attribute listed twice because it is used in the join result, once for the student, another for the takes, even though their ID values must be the same. And in fact, the above query is equivalent to the following query that generates exactly the same results. That is, select asterisk from student takes where student ID equals to takes.id. As we have seen earlier, the relation name is used to differentiate the attributes name ID, and therefore the two occurrences can be referred to as the student.id and the takes.id respectively. And the version of this query that displayed the ID value only one, that means we are using the distinct keywords. So select student.id as ID, name, department name, total credit, course ID, section ID, semester, year, grade. So we are specifying the fields over here. From student, that is joined with the text. What is the condition? That is ID of the student is equals to the text.id. Then on condition can express any SQL predicate. Therefore, a join expression will use on condition can express with a richer scale of the join condition than the natural joins. Now next is the outer join. So suppose we want to display a list of the students displaying their IDs and the names, department name, total credit along with the courses that they have taken. So the following SQL query may appear to retrieve the required information. Select a string from student, natural join takes. And unfortunately, the above query does not work quite as intended. Suppose there is some student who takes no courses, then the tuple in the student relation for that particular student would not satisfy the condition of a natural join with any tuple in that takes relation, and the student data would not appear in the result. Therefore, others will not see any information about the student who have not taken the ID, who have not taken any courses. For example, in the student and the text relation of figure 4.1, 4.2, that students know with the ID have not taken any courses, and the snow appears in the student, but snow's ID number does not appear in the ID column of the text. Therefore, the snow does not appear in the result of the natural join. More generally, some tuples in either or both the relations being joined may be lost in this way. And the outer join operation works in a manner similar to the join operation that we already discussed over here, but we preserve those tuples that would be lost in a join by creating the tuples in the result containing null values. For example, if I want to ensure that the student name Snow from our earlier example appears in the result, therefore a tuple could be added to the join result. That is, we are using the Snow, we are using the text, we are using the course ID, section ID, semester. And there are in fact three forms of outer join. One is a left outer join, one is a right outer join, one is a full outer join. Now let's start with the joins again. So first one is the left outer join that preserves the tuple only in a relation named before to the left of the relation or to the left of the left outer join operation. Then the next is right outer join that preserves the tuples only in the relation named after. So one is a before, one is a after. Then full preserves the tuple in both the relation. That may be a one relation, that may be a one table, that may be a next table. And in contrast, the join operations we studied earlier that do not preserve a non-matched character or the non-matched tuples are known as the inner join operation to differentiate with the outer join. So outer join, left, right join, left join, left, right join, right, full means both the tuples. And first complete the result of the inner join as at before, therefore, or then for every tuple t in the left hand side relation that does not match any tuple in the right hand side in the inner join, that adds a tuple r to the result of the join constructed as follows. The attributes of the tuple R that are derived from the left hand side relation are filled in with the values from the tuple T. And the remaining attributes of the R are filled with the null values. Figure 4.4 shows the result of this, that is select asterisk from student natural left outer join takes. That results include students no, unlike the result of an outer join, but the tuple for the snow includes null for the attribute that appears only in the schema for the takes relation. And as with another example of the use of the outer join, we can write the query, that is find all the students who do not take the course as select ID from student natural left outer join takes where course ID is null. So the right outer join is symmetric to the left outer join, and the tuples from the right hand side relation that does not match any tuple in the left outer join left hand side operation or relation are padded with the nulls and are added to the result of the right outer join. Therefore, if we rewrite our above query using the right outer join and swapping the order in which we list the relations is as follows. So select asterisk from takes natural join right outer join student. So we get the same result except for the order in which the attributes appear in the result. Then full outer join is a combination of the left and the right. That means left hand side is also available, right hand side join is also available. That means yes, full outer join. And as a result of the inner join, it extends with the null values. from the left hand side relation that does not match with any way from the table. Now there is a join operations also. So the on clause can be used with the outer joins, and the following query is identical to the first query as we saw using the student natural left join outer join takes, except that the attribute ID appears twice in the result. So select asterisk from student left outer join takes on student.id equals to takes.id. And as we noted earlier, on and where behave differently for the outer join, and the reason for this is the outer join adds null padded tuples only for those tuples that do not contribute to the result of the corresponding inner join. And the on condition is apart to the outer join specification, but when you say about the where clause, that is not available with the on condition. And in our example, the case of the student tuple for students know with ID 70557 illustrate this distinction. And suppose we modify the preceding query by moving on clause with the predicate to the where clause, and instead using on the on condition of the true. Select asterisk from student left after join takes on true where student.id equals to takes.id. So these are the join types: inner join, left after join, right after join, full after join. Then join conditions, natural, on, using. And the earlier query using the left outer join with the on condition includes a tuple 70557. There's no for 60 null values because there's no tuple in takes with the ID 70557. However, every tuple satisfies the join condition also true. So the no null padded tuples are generated by the outer join. So in the later query, however, every tuple satisfies the join operation. That condition is true. So the not null padded tuples are generated by the outer join. And the outer join actually generates the Cartesian product of the two relations. Since there is no tuple in takes with the ID 70557, every time a tuple appears in the outer join with the name equals to snow, and the values for the student.id takes.id must be different, such that the tuples would be eliminated by the where clause predicate. Therefore, the student's no never appears in the result of the later query. The next is the join types and the conditions. So to differentiate the normal joins from outer joins, normal joins are known as the inner joins in the SQL, and that can be used to specify the inner join instead of the outer join to specify a normal join that is to be used. Keyword inner is however optional, and the default join type join clause is used without the outer prefix, that is the inner join. Therefore, select asterisk from student join takes using ID. The next, yes, join is over. Next part is a view. So in an example up to this point, we have operated the logical model level. Therefore, we have assumed that the relation in the collection we are given are the actual relations stored in the database. So it is not desirable for all the users to see the entire logical model. Security consideration may also require that certain data has to be hidden from the users. Consider a clerk who needs to know an instructor ID, name, department name, but does not have authorization to see the instructor salary amount. So this person could see a relation that is described over here. Select ID, name, department name from instructors. And aside from the security concern, we may wish to create a personalized collection of the relation that is better matched to a certain user intention or the intuition that is in the logical model. And we want to have a list of all the codes specified offered by the physics department in the fall 2009. Then select course ID, section ID, building room number from course section where course.course ID equals to section.course ID and course.department name physics, semester 4, year 2009. The next is a view definition that is defined with the view in by using the create view command. And to define a view, we must give a view a name and must state the query that computes the view. And the form of creating the view command is over here. So this is create view maybe as a query expression, where the query expression is a logical query expression and the view name is represented by the view. Consider again the clerk who needs to access all the data in the instructor relation. Except the salary, the clerk should not be authorized to access the instructor relation. Instead, that is used with the view relation faculty that may be made available to the clerk with the view defined as follows. So create view faculty as select ID, name, department name of instructor. And explained earlier, the view relation is conceptually contains the tuples in the query result but is not pre-computed and stored. Instead, the database system stores the query expression associated with the view relation. Whenever the view relation is accessed, its tuples are created by computing the query result. Therefore, thus the view relation is created whenever it is needed on the demand. To create a view that lists all the course section offered by the physics department in the semester 2009 semester with the building and the room number of each and every section, so we write the query create view physics for 2009 as select course ID, section ID, room number, building from course and section where course ID equals to section row course ID. Now next is using the views in the SQL query. So select course ID from physics for 2009 where building equals to beds. And view names may be appear in a query any place where the relation name appears, and the attribute names of a view can be specified explicitly as follows. So this is create view department total salary, department name total salary as select department name sum salary from instructor grouped by the department. The preceding view gives for each department the sum of all the salaries of all the instructors at that department. And since the expression sum salary does not have any name, so it is specified or it is known as a view definition. And one view may be used in the expression defining another view. For example, we can define a view physics fall 2009 medicine that lists the course ID, room number of all physics courses offered in the fall 2009 semester in the medicine building as follows. Create view physics fall 2009 medicine as select course ID, room number from physics fall 2009 where building equals to medicine. Next is a materialized view. So as per my requirement, we are making the views in which the view relation are stored, but they make sure that if the actual relations used in the view condition changes, the view is kept up to date. Such views are known as a materialized view. For example, consider the view department total salary, and if the above view is materialized, its results would be stored in the database. However, if an instructor tuple is added to or deleted from the instructor relation, yes, then the result would be changed. Why it is changed? Because we are creating the view earlier that is a different view. Now it is a different view. It is changed as per the new requirement. Similarly, if the instructor salary is updated, so the tuple in the department total salary correspond to that instructor department must be updated. That means if there are changes in the instructor department or the instructor salary, then automatically it will change over here. And the process of keeping the materialized view up to date is known as a materialized view maintenance. The update of the view. So insert into faculty values. So we are changing or making the views definition. So when we update of the view, that is used with the insert into faculty values 30757, then green, then music. So the insertion will be used represented by the insertion in the relation. Since instructor is the actual relation from which the database system must construct the view faculty, and however to insert a tuple into the instructor, we must have the same value for the salary. And there are two possible reasons why it is used with this one. So reject the insertion and returns an error message to the user, then insert a tuple with the relation in the instructor relation. So reject the insertion, returns an error message to the user, insert a tuple as 30765 green music null into the instructor relation. Another problem with the modification that occurs with the create view instructor info as select ID name building from name or ID name and the building. then where department or whether instructor dot department name equals to department dot department name. So this is create view instructor info as select ID name building from instructor department where instructor dot department name equals to department dot department name. And this view lists the ID, name, building, name of each instructor in the university.